Draw a triangle across the whole sky, corner to corner. Its three angles almost add to 180 degrees. That means space is almost perfectly flat on cosmic scales. You can test the universe with geometry, not rockets. Shape here means curvature and any global wraparound of space. We can measure it using the oldest light in existence. The immediate takeaway: the universe looks astonishingly flat overall. Flat does not mean boring, space could still loop around. Light, sound, and galaxies reveal that hidden shape today. Tiny test. Do parallel beams stay parallel across billions? Their answer sets distances, ages, and even cosmic destiny. So let's draw that triangle with light as our ruler. Stand on a salt flat under a cold, starry night. The horizon looks straight, and parallel tire tracks never meet. Shape, in cosmology, means the curvature and topology of space. Curvature says how straight lines bend or fail to bend. Topology asks whether space connects back on itself like a loop. This matters because geometry controls distances, volumes, and cosmic fate. In curved spaces, triangles cheat on the classroom rule. On a sphere, the angles add to more than 180. On a saddle, they add to less than 180. In truly flat space, they add to exactly 180. Here is how it works using straightest possible paths called geodesics. Positive curvature squeezes geodesics together, while negative curvature sprays them apart. Zero curvature keeps them parallel forever, at least ideally. Example in real terms: shine two lasers across intergalactic space. After 1 billion light years, do they converge, diverge, or stay aligned? That one comparison encodes the sign of curvature. Rule of thumb: triangles big enough reveal the true geometry. So the picture is, shape means curvature plus possible global wrap. Now freeze the universe when it was a glowing fog. That afterglow is the cosmic microwave background, the oldest light we see. It is a baby picture of density ripples, frozen in time. Why it matters: that pattern is an enormous built-in ruler. Sound waves rang through the young plasma like ripples on water. They reached a maximum size before light finally streamed freely. That size is the sound horizon, a known physical length. Light crossed it, so we know its scale in megaparsecs. Here is the move: measure its angular size on the sky. In flat space, that standard ruler spans about 1 degree. In curved space, the same ruler looks bigger or smaller. Positive curvature makes it appear larger, while negative makes it smaller. Satellites map the peaks and troughs of that pattern precisely. The first acoustic peak lands near that 1 degree mark. That placement tells us space is astonishingly close to flat. Quick recap: we read cosmic geometry by comparing size to angle. So the bottom line: the sky's baby photo carries a protractor. Pan out to the cosmic web, bright nodes linked by faint filaments. Galaxies are not random, they prefer certain spacings, like ripples. Those ripples are called baryon acoustic oscillations, cousins of the CMB waves. They left a preferred separation imprinted in the galaxy distribution. The physical scale matches the early sound horizon, set in plasma. Why care? A second ruler double-checks space without using the microwave glow. Survey teams map millions of galaxies across huge patches of sky. They count pairs by separation, then look for a gentle bump. That bump appears near 150 million parsecs in moving distance. Compare its apparent size to the known physical scale. In flat space, the math lines up cleanly across redshifts. Curvature would shift angles and distances unevenly with time. Observations show the bump where flat geometry predicts it. Different surveys agree, despite different telescopes and target selections. That redundancy slams the door on many curved alternatives. One-sentence recap: galaxies write the same 1 degree story in kilometers. Zoom into a control room of the sky, lit by stars. Data pour in from Planck, WMAP, and galaxy surveys worldwide. Combine them, and you can weigh cosmic curvature directly. The result points to zero curvature within tight error bars. Think within a few parts per thousand, either way. You can phrase it as the curvature density parameter, omega k. It sits extremely close to zero, with tiny allowed wiggles. There is always room for systematic errors or subtle correlations. Researchers test that by mixing independent datasets carefully and repeatedly. Add gravitational lensing of the microwave background for another cross-check. Its gentle smearing prefers near-flat models over curved ones. Even with caution, the same answer keeps returning again and again. Example number: that standard ruler still lands near 1 degree today. That consistency across redshifts nails down geometry better than any one probe. Net result, our observable patch looks flat to impressive precision. Bottom line, flat is not a guess, it is measured. Shift from curvature to the deeper question, could space still loop? A room can be flat inside, yet wrap around globally. Topology studies those wraparound possibilities without changing local straightness. Picture a three-dimensional torus, the 3D cousin of a donut. Travel straight, and you eventually return to your starting point. No wall, no edge, just repeating directions stitched together seamlessly. Why it matters, a finite space changes what we could observe. Paths of light could circle around, showing repeating sky patterns. Here is how astronomers hunt for that subtle sign. They search the microwave background for matching circles on opposite sides. If the universe repeats, patterns should align across those mirrored rings. Teams have looked hard, using Planck's high-resolution sky maps. So far, no convincing matched circles have survived the tests. That means any wraparound scale is larger than our visible patch. Example number, the fundamental domain must exceed tens of billions of light years. One sentence recap, space could loop, but the loop seems very large. Stand on an endless beach and ask where the ocean ends. People often ask whether space has an edge or center. In standard cosmology, it has neither, even if space were finite. Every point can look like the center by symmetry. Edges would cause special directions, which observations simply do not show. The balloon metaphor helps as long as you hold one caution. Ants walking the balloon feel curved but never find an edge. There is no center on the surface, only curvature everywhere. Our universe would be the three-dimensional analog of that surface. The center of expansion is not a place, it is a property. Distances grow between all far-apart points, carried by expanding space. Galaxies are not flying through air, the air itself stretches. Example in real terms, every megaparsec expands by about 70 kilometers per second. That rate today is the Hubble constant we infer. Net result, no edge and no center are needed at all. Roll the clock back to a hot, dense, nearly uniform fireball. Small ripples grew under gravity, while space itself expanded. Inflation likely happened earlier, stretching space by stupendous factors. That burst irons out curvature, like steaming a wrinkled shirt. A nearly flat universe naturally falls out of that process. Why it matters, curvature also ties into cosmic destiny. Old textbooks linked closed universes to recollapse and open to endless expansion. Dark energy breaks that link by accelerating expansion today. Even a slightly closed universe could still expand forever with dark energy. Mechanically, cosmic shape evolves with energy contents as the universe dilutes. Radiation fades fastest, matter next, while dark energy stays stubborn. The curvature fraction gets driven towards zero during inflation and after. Example scale, inflation may stretch by factors near 10 to the power of 60. That makes any initial curvature absurdly tiny within our horizon. So the picture is, inflation plus observations explains near-flat space today. Remember that sky-spanning triangle from the start, with nearly normal angles. We measured it using ancient light, galaxy ripples, and lensing. The answer we keep getting is simple but profound. Our universe appears flat, and any global loop must be huge. That is the payoff you can carry out the door. If this cracked a question you have carried around, consider subscribing. I make deep space clear without the chalk dust and jargon. One new video each week, always anchored in measured reality. Drop your wild follow-up question in the comments, I read them. Until next time, keep that cosmic protractor handy and look up.